On a cold night in 1923, high above Los Angeles at the Mount Wilson Observatory, Edwin Hubble leaned over a glass photographic plate and noticed something unusual in the faint haze of the Andromeda Nebula. He marked a tiny point of light with a simple note, VAR, short for variable star. It was an ordinary pencil mark, quiet and practical, the kind that could disappear into an archive without ceremony. Yet in that moment, one of the oldest human assumptions about the universe began to fail. Imagine the stillness inside that dome for a moment. The telescope had done its work hours earlier. Now the task was slower, more intimate, and strangely fragile. A patch of light on a plate, a measured change in brightness, a chain of reasoning built by other minds in other rooms over many years. If that star was truly the kind Hubble suspected, then Andromeda was not a small cloud inside the Milky Way. It was something far more distant, far more immense, a world of stars in its own right. The universe was not merely larger than expected. It belonged to a different order of size altogether. That is the deeper story of this documentary. Not simply the search for a number, but the history of a question that kept slipping away from every answer. Each generation believed it had found the scale of the cosmos, only to discover that the horizon had moved again. The nearest stars opened into the galaxy. The galaxy opened into other galaxies. The visible heavens opened into an expanding universe. And the expanding universe opened into a reality whose true extent may still lie beyond anything we can ever observe directly. So how did human beings, working with dim stars, flawed instruments, stubborn theories, and often very human rivalries, begin to measure something so vast that the mind resists it? And when we ask how big the universe really is, are we asking for a distance? Or are we confronting the edge of what a species like ours can ever know? If you ask how big the universe is, the question seems, at first, almost innocent. It sounds like the kind of question a child might ask after looking up at the night sky, or the kind of question that appears in the quiet middle of a sleepless evening, when the mind drifts outward and begins to wonder where anything really ends. For a long time, many people have imagined that science must already possess a final, polished answer, some immense number waiting at the back of a textbook, like the solution to a completed equation. Yet this is one of those rare questions that becomes stranger the closer you bring it to the light. Modern cosmology can describe the age of the universe with remarkable confidence. It can estimate the scale of the part we are able to observe. It can model the large structure of space with extraordinary mathematical care. And still, when we ask how big the universe really is, we are no longer asking for just one number. We are stepping into a question with layers, and each layer changes what the word size is allowed to mean. The confusion begins in a very human way, with intuition. If the universe is about 13.8 billion years old, then it seems natural to imagine that the furthest thing we could possibly see should lie 13.8 billion light years away. Light travels 1 light year in 1 year. The arithmetic appears simple, almost comforting. But the universe has never been obliged to fit comfortably inside the patterns of ordinary thought. Between the moment when ancient light began its journey toward us and the moment it entered our telescopes, the fabric of space itself continued to change. Galaxies were not sitting still while light crossed a fixed cosmic stage. The stage was stretching. That means the most distant regions, whose light has reached us today, are not merely 13.8 billion light years away in the ordinary sense. In modern cosmology, the radius of the observable universe is closer to 46 billion light years, which means the full observable diameter is roughly 93 billion light years across. The first surprise of this documentary, then, is not simply that the universe is large, it is that the words we use for distance must bend, before the universe can even begin to answer us. This is the point at which the question divides. There is the age of the universe, which tells us how long it has existed in its present expanding form. There is the observable universe, meaning the region from which light, or any signal traveling at the speed of light, has had time to reach us since the cosmic beginning. And then there is something more elusive, the total universe, which may extend far beyond what we can ever observe. These are not 3 different opinions about the same thing. They are 3 different levels of the same mystery. The age of the universe is not the same as its width. The observable universe is not necessarily the same as the whole universe, and the whole universe may include regions so distant that no future telescope, no matter how refined, could ever bring them into view. Once that distinction enters the story, the question grows quieter, deeper, and more unsettling. We are no longer just asking how far the cosmos extends. We are asking how much of reality is even in principle available to a creature like us. There is something psychologically revealing in the fact that this question resists simplification. Human beings evolved among hills, shorelines, seasons, and distances measured by walking, sailing, and eventually by maps. Even the great architectural and imperial scales of history remain tied to the size of a body moving through a world. The mind is good at local space. It can imagine valleys, continents, oceans, and perhaps, with some effort, the gap between planets. But cosmological space is different. It is not merely more of the same. It introduces scales at which ordinary intuition fails, then asks us to keep thinking anyway. One of the quiet achievements of science is not that it makes the universe small enough to grasp, but that it teaches the mind how to remain calm in the presence of what it cannot naturally picture. This is part of the emotional texture of cosmology. Beneath the equations and instruments, there is always a human nervous system trying to orient itself inside a reality that did not evolve to feel familiar. For that reason, the history of measuring the universe is also a history of correcting the imagination. Again and again, people believed they had found the boundary of the world that mattered, only to discover that the boundary was only temporary, or only local, or only the limit of their present tools. Yet before we reach those turning points, it helps to stay a little longer with the modern form of the question itself, because it contains one of the central lessons of the whole film. In everyday speech, the universe sounds like a single object, perhaps the largest object imaginable, a kind of cosmic container that either has an edge or does not. In scientific thought, however, the word operates more carefully. Sometimes it means the whole of physical reality. Sometimes it refers to the expanding space-time described by cosmology. Sometimes, in practice, it means the part whose properties can be inferred from observation. Those meanings overlap, but they are not identical. Even the most advanced cosmological models proceed with a kind of disciplined humility. They say, in effect, this is what we can infer about the region we can see, and from that, perhaps, this is what we may cautiously imagine about the rest. That caution matters, because the universe does not present itself to us all at once. We never stand outside it. We never look at it from a distance. Every observation we make is local, delayed, and shaped by light that takes time to arrive. To observe the distant universe is to look backward in time. The night sky is not a picture of simultaneous existence. It is a layered archive. Nearby stars appear roughly as they were years ago. Distant galaxies appear as they were millions, even billions of years in the past. The deeper we look, the older the light becomes. By the time our instruments detect the faint afterglow of the early cosmos, we are no longer seeing a distant place in the ordinary sense. We are seeing an early state of the universe itself. This is why cosmology feels so unlike common experience. Distance becomes history. Looking outward becomes looking backward. Size becomes inseparable from time. And then another complication arrives. Even if we know the age of the universe, and even if we can map the observable part with astonishing detail, we still do not know with certainty whether the total universe is finite or infinite. This is one of those moments where popular curiosity runs directly into the edge of present knowledge. Many people assume that modern cosmology must have settled the matter by now. In reality, the answer remains open. Observations suggest that space on the largest scales appears very close to flat, but flatness does not, by itself, force a simple conclusion that the whole universe must be infinite in a neatly intuitive way. A flat universe can be infinite in standard models, but what can actually be established from observation is more limited. We know the visible region is enormous. We know the large-scale geometry appears extremely close to flat. We know the cosmos has expanded for billions of years, and that the part accessible to us has a measurable history. Yet the totality, the full extent of everything beyond our cosmic horizon, remains hidden behind the oldest barrier in science. Not a lack of intelligence, but a lack of access. This distinction between the observable and the whole is one of the most beautiful and unsettling consequences of modern cosmology. It reminds us that science is not a magical removal of all mystery. It is a disciplined way of separating what can be known, what can be inferred, and what must remain uncertain for now. In that sense, the size of the universe is not just a technical question. It becomes a philosophical test of scientific maturity. A less careful culture of thought wants quick absolutes. It wants either a neat, finite boundary or the thrill of declaring infinity with confidence. Cosmology has learned to be more restrained. It says, here is the horizon of observation. Here is what the fossil light of the early universe tells us. Here is how expansion alters our notion of distance. Here is what geometry seems to suggest. And here, beyond that, lies the territory where our best models continue, but our evidence grows thin. There is something profoundly honest in that posture. It does not weaken science. It is one of the reasons science deserves trust. Still, it would be wrong to imagine that this careful modern understanding arrived fully formed. The distinctions that now seem elegant were hard-won. They emerged from generations of confusion, failed assumptions, improved instruments, revised theories, and very human habits of overconfidence. Even the language of cosmology carries traces of that struggle. Terms like horizon, expansion, distance, age, curvature, and observable all had to become more precise because older intuitions kept breaking under the weight of new evidence. In a way, the modern answer to how big the universe is has the shape. It does precisely because simpler answers failed. That is why this opening chapter matters. Before we begin moving through observatories, debates, equations, and discoveries, we need to understand that the difficulty is not just in the measuring. The difficulty is built into the question itself. We are asking for the size of a reality from within that reality, using signals that arrive slowly from a universe whose very geometry and history are part of the answer. Picture, for a moment, what this means at a human scale. Somewhere tonight, a person stands outside beneath a dark sky and looks up. Perhaps there is a single bright planet low above the horizon. Perhaps only a scattering of stars between city lights. Perhaps a clear country sky dense with cold points of light. The feeling is ancient, but the conceptual world behind it has changed almost beyond recognition. Those stars are not pinned to a celestial shell. The darkness between them is not empty in the old, simple sense. The sky is not a ceiling, but an opening into a deep, expanding history. Some of the light arriving now began its journey before human civilization existed. Some of it comes from galaxies so distant that the space between us and them has stretched dramatically while the light was still en route. And beyond what we can see, there may be more galaxies, more structure, more space, or perhaps something stranger than any of those words can hold. The ordinary act of looking up has become, in modern knowledge, an encounter with limits, both cosmic and cognitive. There is also a quiet irony here. The more exact our measurements become, the more clearly we see that size is not the kind of property we can simply read off the universe, like the height of a building or the length of a road, We must choose a definition, and that choice depends on what aspect of the universe we are trying to describe. Are we asking how old it is? How far light has traveled? How far away the source is now? After expansion, how large the visible region has become? Whether the whole extends beyond that region without bound? Each answer is meaningful within its own frame, and each can sound misleading when detached from that frame. This is why even skilled communicators sometimes stumble when they try to compress cosmology into a single headline. The subject punishes oversimplification, yet it rewards patience. Once the distinctions settle in the mind, a richer and more truthful picture appears. The universe becomes harder to summarize, but easier to respect. So, this first chapter does not end with a final measurement. It ends, more properly, with a clearing of the ground. We now know that the question before us is not small, not simple, and not purely numerical. It belongs partly to astronomy, partly to physics, partly to the history of ideas, and partly to the study of how human beings learn to think beyond the scale of their own instincts. We know that there is an age of the universe, a size for the observable cosmos, and an open question about the total extent of reality beyond what light has allowed us to see. We know that distance and time are woven together, that space itself can expand, and that the universe may remain larger than any answer we can presently defend with certainty. But before scientists could speak this way, before horizons and background radiation and cosmic geometry entered the story, humanity had to begin somewhere else. It had to begin with the old instinct that the world must have a shape simple enough to imagine, perhaps even a boundary firm enough to picture. And so, having untangled the question in its modern form, we can now turn back to an earlier age, when the universe still seemed to have walls. And so, the story turns back toward an older sky, one that seemed not merely vast, but finished. In the cosmology that shaped learned thought for centuries, the universe was not an open question stretching into indefinite depth. It was an ordered whole. Aristotle placed Earth at the center, surrounded by nested heavenly spheres, and argued that the material universe had to be finite rather than spatially unbounded. He also rejected the notion of actual infinity in the physical world, allowing instead only a kind of potential infinity in processes such as counting or the succession of days. In that picture, the cosmos was complete, structured, and enclosed within a rational architecture. It was large enough to inspire awe, but not so large that it escaped form. What made that old universe so persuasive was not only philosophy, but experience. Everything in ordinary life seemed to encourage the belief that things had natural places and proper motions. Stones fell, flames rose, seasons repeated, and the heavens turned with a regularity unlike anything on Earth. Aristotle's cosmos drew a deep boundary between the changing world below the moon and the more perfect heavens above it, where celestial bodies were thought to move in enduring circular paths. Even transient things like comets were commonly treated in that tradition as atmospheric phenomena, rather than true residents of the higher heavens. The result was a picture of reality in which the sky did not invite endless speculation, so much as steady contemplation. It had layers, rank, and closure. For the human imagination, that closure mattered. A universe with walls is easier to inhabit than one without them. Over time, this sense of cosmic enclosure became more than a scientific model. It became part of a wider habit of thought. Medieval scholars inherited much of the Aristotelian framework, blending it with theological interpretation and with the practical astronomy needed for calendars, navigation, and ritual timekeeping. The heavens were not merely a place where stars happened to be. They formed a meaningful order. To describe the cosmos was also, in some sense, to describe the structure of reality itself. The appeal of such a system helps explain why it endured for so long. It satisfied reason, authority, and intuition all at once. And when a worldview achieves that kind of balance, it is rarely abandoned because of abstract doubt alone. It has to be pressured, piece by piece, by observations that refuse to stay inside it. When the Copernican system emerged in the 16th century, it did not immediately shatter those old walls. In some respects, it left them standing. Copernicus moved Earth away from the center and placed the sun at the heart of planetary motion. But the broader universe around that new arrangement was still imagined in bounded and orderly terms. The more troubling consequence of heliocentrism lay elsewhere. If Earth really moved around the sun, then the stars should appear to shift their positions over the course of the year when seen from different points in Earth's orbit. This effect, stellar parallax, was expected in principle, and its absence became one of the most serious astronomical objections to a moving Earth. Copernicus and his contemporaries could detect no such shift. That left only two broad possibilities. Either Earth did not move, or the stars were at such immense distances that their annual displacement was too small to detect. A sun-centered cosmos could be saved, but only at the cost of enlarging the stellar realm to a scale many found almost absurd. That tension helps explain the peculiar importance of Tycho Brahe. He was one of the finest observational astronomers of the age, and he stood at a threshold where the old heavens began to show cracks without yet collapsing into the new universe to come. In 1572, he observed the brilliant new star, now known as Tycho's supernova, and concluded, from the lack of detectable parallax, that it lay among the fixed stars rather than in the changing atmosphere below the moon. 5 years later, the Great Comet of 1577 raised another difficulty for inherited cosmology. In older traditions, comets had often been assigned to the atmosphere, but the new measurements suggested this object lay much farther out. Tycho's work did not immediately produce a modern universe, yet it did something equally important. It weakened the confidence with which people had divided heaven from weather, permanence from change, sphere from open passage. Still, Tycho did not accept Earth's motion. The missing stellar parallax continued to trouble him, and he proposed instead a hybrid system in which the sun orbited Earth while the other planets orbited the sun. It was an ingenious compromise, born from a sky that had become less stable, but not yet deep enough to force a final choice. the telescope added a new kind of pressure. When Galileo turned it toward the Milky Way in the early 17th century, the pale luminous band was no longer just a cloudy streak across the night. It resolved into a multitude of faint stars. He also reported that the telescope revealed far more stars than the naked eye could see. This did not yet tell astronomers how far away those stars were, and it did not by itself prove heliocentrism, but it transformed the feel of the sky. A fixed shell, ornamented with lights, began to look more like a crowded region extending beyond ordinary vision. The heavens acquired texture. They became populous in a new way. At the same time, Galileo's telescopic discoveries around Jupiter and Venus showed that not everything in the cosmos revolved around Earth, and that appearances once treated as final were vulnerable to improved observation. The old walls had not vanished, but they had started to look less like the boundary of reality and more like the boundary of unaided sight. This growing depth of the heavens created a more subtle problem, one that entered the history of cosmology almost as a thought lingering at the edge of observation. If the universe were truly limitless and filled indefinitely with stars, why was the night sky dark? Johannes Kepler raised a version of that question in 1610. As an argument against an infinite universe of stars, and later centuries would remember the puzzle under the name of Olbers. The logic, once stated plainly, is disarming. In an eternal and static universe, uniformly populated with luminous stars, every line of sight should eventually end on a stellar surface. Distance would dim individual stars, but more distant shells of space would contain proportionally more of them. The darkness of night would become difficult to explain. Kepler did not possess the modern solution, and neither did Olbers, but the question itself mattered because it showed that cosmic scale could not be treated as a neutral backdrop. The size, age, and structure of the universe were beginning to place demands on one another. Even the darkness overhead had become evidence. Yet the most direct test of a moving Earth remained the one that still would not yield. If Earth circled the sun, a nearby star should seem to shift slightly against more distant background stars when viewed 6 months apart. The principle is easy enough to picture in everyday life. Hold out a hand and close one eye, then the other, and the hand appears to move against the wall beyond it. Astronomy asked for the same effect on a vastly smaller angular scale, using the diameter of Earth's orbit as the baseline and the stars as the distant objects. This was conceptually simple and technically brutal. The stars were so far away that the expected shifts were minute, far below the reach of early instruments. For generations, astronomers chased the effect and reported results that could not survive scrutiny. The problem was not merely one of patience, it was one of precision, stability, and the difficulty of telling a real stellar shift from the imperfections of instruments, atmosphere, and the observer's own eye. In the 18th century, this search produced an unexpected reward before it produced its intended one. James Bradley, working in the 1720s, was investigating apparent stellar displacements when he realized that the motion he saw was not parallax in the strict sense. It behaved differently. The explanation he eventually offered was the aberration of light, an effect caused by the finite speed of light combined with Earth's motion through space. The star was not changing position because of varying viewpoint alone. Rather, the apparent direction of incoming starlight was altered by the motion of the observer. Bradley announced the discovery in the late 1720s, and it became one of the strongest early observational supports for Earth's orbital motion. This was a remarkable turn in the story. Astronomers had set out to measure the stars, and instead found a new phenomenon linking light, motion, and observation. The heavens had withheld one answer and given another. Even in failure, the universe was becoming more intelligible. Still, aberration was not distance. It confirmed that Earth moved, but it did not tell astronomers how far away the stars really were. The original prize remained just out of reach. To obtain true stellar parallax, an observer had to track a nearby star relative to much more distant ones and detect an annual change so small that it would amount to a fraction of an arcsecond, an angle tiny beyond everyday comprehension. This is where the history of cosmology becomes inseparable from the history of precision measurement. The universe was no longer being challenged only by new theories. It was being challenged by improved hardware, better calibration, more careful statistics, and a growing willingness to distrust attractive results if they emerged too easily. In a sense, the walls of the old universe were not pushed outward by imagination alone. They were worn down by methods. Every improvement in angular measurement made it harder for a small cosmos to hide behind observational uncertainty. The decisive breakthrough came in 1838 with Friedrich Wilhelm Bessel. He chose 61 Cygni, a star already known for its unusually large proper motion across the sky, reasoning that such motion might indicate relative nearness. Using a heliometer built by Joseph von Fraunhofer, Bessel measured the star's tiny annual shift against neighboring stars and published the first reliable stellar parallax. The effect was extraordinarily small, but it was enough. Almost at once, the stars ceased to be only a decorative background or a philosophical category. They became objects situated in measurable depth. Around the same time, Thomas Henderson and Friedrich Georg Wilhelm von Struve also obtained early trustworthy results for Alpha Centauri and Vega, which shows that this achievement was not an isolated accident, but the result of astronomy finally reaching the necessary level of precision. Yet Bessel's result remains symbolically central because it marked the moment when a question that had haunted the Copernican system for centuries was answered with numbers. The Earth moved, the stars were staggeringly distant, and the old objection, based on missing parallax, dissolved into a new fact about the scale of the universe. It is difficult to overstate what changed in that moment. The measured parallax of 61 Cygni did not make the universe suddenly modern, and it certainly did not reveal its full size. What it did was quieter and, in some ways, more profound. It established that the stars occupy real, three-dimensional distances that can be derived from geometry. A triangle drawn from Earth's orbit, once treated as a promise of future proof, had become an instrument for stepping into the cosmos. The sky was no longer a surface. It had depth, and with depth came a different kind of intellectual responsibility. Once one star could be measured, the stars as a whole could no longer remain a symbolic backdrop to human life or philosophy. They had become a domain for exact inquiry. The universe still felt immense, but now its immensity had begun to acquire structure. This is often how revolutions in understanding truly happen, not when mystery disappears, but when mystery becomes measurable. By the middle of the 19th century, the ancient walls had not entirely vanished from memory, but they could no longer hold. Aristotle's enclosed cosmos had yielded, step by step, to a universe in which the stars were far beyond old expectation, and no celestial shell could contain them in any simple sense. Yet that victory came with a new limitation. Parallax could reach only the nearest stars. It proved that the heavens had depth, but it did not tell astronomers how to cross that depth systematically, or how to push beyond the immediate stellar neighborhood into the larger architecture of the cosmos. The wall had been broken, but there was still no staircase. To go farther, science would need something more than a geometric foothold. It would need a way to build distance into a ladder, rung by rung, until even the deeper dark could be measured. That staircase, when it finally began to appear, did not rise in one grand piece from the earth into the stars. It was assembled slowly, rung by people who often worked far from the public image of heroic astronomy. The great observatory dome, with its turning machinery and cold night air, remained part of the story. But another kind of room now mattered just as much. Inside offices and plate stacks, under steady indoor light, astronomers learned to read the sky after the fact, not as a momentary spectacle, but as a record. What the eye had once seen and lost, the photographic plate could preserve, and once the sky could be preserved, it could also be compared, measured, and returned to patiently until tiny regularities emerged from what had once looked like scattered light. The universe, which had resisted direct measurement on its largest scales, began to yield not through a single bold leap, but through a new style of scientific attention. It was in that quieter world that Henrietta Swan Leavitt did her most important work, at Harvard College Observatory, where women working as astronomical computers examined and organized the growing flood of photographic data. Leavitt belonged to a generation of highly skilled researchers whose labor was essential to modern astronomy and yet long treated as background. Edward Pickering's observatory had become a place where the sky was not only observed, but sorted, classified, and quantified. Plates arrived from different instruments and from different sites, including Harvard's Southern Station in Arequipa, Peru, extending the observatory's reach into regions of sky that Cambridge itself could not fully study. Leavitt's task was not glamorous in the popular sense. She compared the brightness of stars across repeated images, looking for patterns that only became visible through repetition. It was careful work, almost monastic in its discipline, and for that very reason, it was exactly the kind of work from which a durable discovery could grow. At first, variable stars were less an answer than a complication. The older astronomical ideal had often favored permanence, stars as stable fixed points against which motion elsewhere might be measured. But the sky kept offering objects that brightened and dimmed. Some did so irregularly, some in patterns, and some with a striking fidelity that suggested an internal rhythm not yet understood. To many observers, this variability was interesting, but not obviously transformative. It took a mind like Leavitt's to recognize that a fluctuating star might be more useful than a constant one. Working through repeated photographs of the Magellanic Clouds, she identified large numbers of variables and brought order to what might otherwise have remained a catalog of peculiarities. In 1908, she published results from that work, including hundreds upon hundreds of variable stars, and noted something suggestive among the Cepheid type. The brighter ones seemed to have longer periods. It was not yet a finished law, but it was the beginning of one. The setting of that insight was crucial. Leavitt had been studying stars in the small Magellanic Cloud, and that gave her a special advantage. Although the exact distance to the cloud was not yet known, its stars could reasonably be treated as lying at roughly the same distance from Earth, relative to the much larger differences that separate truly nearby and truly remote stars. That meant their apparent brightnesses could be compared in a meaningful way. If one Cepheid in the same cloud looked brighter than another, the difference was unlikely to arise mainly from one being dramatically nearer than the other. It more likely reflected a difference in the stars themselves. Within that shared setting, a hidden order could reveal itself. In 1912, examining a sample of 25 Cepheid variables in the small Magellanic Cloud, Leavitt showed the relation clearly. The longer the period of pulsation, the greater the intrinsic luminosity. A changing star had become a measuring device. The elegance of the idea becomes clearer the longer one sits with it. A Cepheid does not merely flicker, it pulses with a rhythm that can be timed. Leavitt's breakthrough was to show that this rhythm was linked to the star's true brightness, not just its changing appearance to us. Once that principle is known, a Cepheid becomes something like a coded light source. By measuring its period, an astronomer can infer how luminous it really is. Then, by comparing that intrinsic luminosity with how bright it appears from Earth, the distance can be calculated. The mechanism that makes Cepheids pulsate would only be understood later in astrophysical detail. But Leavitt did not need that later theory to grasp the observational law in front of her. She had found a regularity strong enough to carry cosmic weight. In time, this would become one of astronomy's first great standard candles. Not a direct ruler, but something almost as powerful, a known light by which distance could be judged. Yet the discovery, for all its beauty, arrived with an immediate limitation. Leavitt had found the relation, but not the absolute scale, because the exact distance to the Magellanic Clouds was still uncertain. The law initially lacked a fully fixed calibration. The shape of the staircase had been drawn, but its first rung still needed anchoring. Over the following years, astronomers such as Einar Hertzsprung worked to calibrate the period luminosity relation using Cepheids in the Milky Way, where distance estimates could at least begin to be approached through parallax and statistical methods. Those first calibrations were difficult and not free from error, but they served the essential purpose. They converted Leavitt's relation from a striking pattern into a working instrument. This is one of the recurring truths in the history of science. A discovery is often born in one place and made usable in another. Observation provides the shape, and then later measurement supplies the scale. As a result, something far more ambitious became possible. Astronomers no longer had to rely only on geometric parallax, whose reach ended among the relatively nearby stars. They could begin constructing what would later be called the cosmic distance ladder, a sequence of methods in which one reliable measure was used to calibrate the next. parallax could establish distances to certain nearby stars. Those distances could help calibrate Cephids. Cephids, in turn, could extend distance measurement vastly farther into the galaxy and beyond. The power of this method lay in its cumulative structure. No one measurement reached the universe directly, but each rung, if carefully secured, allowed the next to be attempted. The danger, of course, was that uncertainty could also climb the ladder. A small calibration problem at the bottom might become a large error at the top. Even so, this new strategy changed the scale of astronomy. It offered, for the first time, a plausible way to move from the local neighborhood of stars into the deeper architecture of the cosmos. That deeper architecture soon came into view through the work of Harlow Shapley, who used Cepheid variables and related stellar indicators to estimate distances to globular clusters. What mattered in his work was not only the clusters themselves, but the larger pattern that slowly began to form around them. As their distances were plotted and compared, the Milky Way no longer appeared as a modest, familiar star system with the Sun somewhere near its natural middle. Instead, it began to take on a far more immense and displaced form, one in which our own position seemed less central, less privileged, and far less intuitively satisfying than earlier generations had assumed. A galaxy that had once seemed almost knowable in outline was becoming larger, deeper, and more difficult to hold in the mind. Shapley's calculations suggested that the Milky Way was far larger than many astronomers had previously imagined, and that the Sun was not near its center. This was not a minor adjustment to an already stable picture. It was a change in scale that altered the emotional shape of the cosmos, the familiar stellar system that contained human history, the Earth, and the visible band of the night sky was expanding into something much broader and more asymmetrical than expected. The consequence of that shift was not merely technical. It affected how astronomers imagined their place inside the galaxy itself. The Sun, once easily treated as a natural reference point, began to look more like a local inhabitant of a structure whose true center lay elsewhere. In retrospect, some of Shapley's distances would prove too large, and later corrections would matter greatly. But that does not diminish the force of what his work accomplished at the time. Even where the numbers would later be revised, the intellectual effect was unmistakable. The Milky Way was no longer shrinking into convenience. It was opening outward into a system of far greater scale and complexity than many had been prepared to accept. That enlargement, even in imperfect form, was enough to shift the discussion onto new ground. Once the galaxy had been made larger in thought, older assumptions about its neatness and human-centered orientation became harder to restore. The old familiar Milky Way, once easy to imagine as the main body of the universe, was swelling into something much grander and more structurally complex. Leavitt's discovery did not by itself settle the size of the galaxy, but it made such questions newly tractable. The ladder she helped build was already doing what all powerful scientific tools eventually do. It was not just answering old questions more precisely, it was making larger questions possible. Distances that had once been beyond reach were now part of serious inquiry, and the scale of the galaxy could be argued over with numbers instead of intuition alone. In that sense, the universe was not merely growing in measurement, it was growing in thinkability. There is also a more human layer to this story, one that deserves to remain visible. Leavitt's 1912 paper was communicated under Pickering's authority, and the publication itself notes that it had been prepared by Miss Leavitt. In formal scientific terms, the discovery entered the literature. In cultural terms, however, the path from labor to recognition was less direct. This was common in the world of the Harvard computers, where skilled women carried out demanding analytical work that underpinned much of modern astronomy. Leavitt was not a theatrical self-promoter, nor did history initially rush to place her at the center of the story her work had made possible. She died in 1921, before the full extragalactic consequences of Cepheid measurement became famous in the 1920s. That timing matters. One of the foundational tools for measuring the universe was established by someone who did not live to see the most celebrated use of it. The quietness of the discovery was not incidental. It was part of its history, and perhaps that is why this chapter in science feels so psychologically rich. Popular imagination often prefers discovery in the form of revelation. One person in one dramatic moment seeing what no one else had seen. Leavitt's work belonged to a different rhythm. It emerged from comparison, notation, repetition, and the long patience of noticing that some changes changes repeat with order. There is something almost musical in that kind of attention. A cepheid brightens and fades again. And somewhere inside that recurrence lies a law. To hear such a law in the data requires not only intelligence, but steadiness. It requires trust that meaning may hide in what seems monotonous. In that sense, the period luminosity relation did more than enlarge astronomy. It offered a new lesson in how the universe sometimes reveals itself, not through spectacle, but through disciplined listening to regularity. By the early 20th century, the consequences were already spreading outward. Once astronomers possessed a reliable class of stars whose periods encoded their luminosities, distant systems ceased to be wholly anonymous smudges of light. Some of them might now contain measurable markers. Some might yield their remoteness not through direct geometric triangulation, but through luminous signatures that could be recognized across vast depths of space. The sky was becoming legible in a new way. At the same time, the very success of the latter raised a larger problem. If the Milky Way was much bigger than once believed, and if distance could now be pushed farther than parallax ever allowed, what exactly were the spiral nebulae scattered across the heavens? Were they nearby structures inside our own galaxy, or were they separate stellar systems far beyond it? The staircase had been built far enough to reach a landing. Beyond that landing waited a door that would open onto a far larger universe. Beyond that landing waited a question that had been gathering pressure for years. The spiral nebulae, those faint world patches scattered among the stars, had long occupied an uncertain place in astronomy. Through small telescopes, they appeared as delicate structures, some with a bright center and curved arms, others more diffuse, all of them hovering at the edge of classification. To some observers, they seemed likely to be nearby objects within the Milky Way, perhaps clouds of luminous matter in the process of forming stars or solar systems. To others, their appearance suggested something far more radical. They might be entire stellar systems in their own right, vast assemblages of stars lying far beyond the bounds of our galaxy. This was not merely a dispute over labeling, it was a conflict over the scale of the known universe. If the spirals belonged to the Milky Way, then the galaxy might still be, in some practical sense, the whole of the cosmos. If they lay beyond it, then the sky was opening onto an order of magnitude that had scarcely been absorbed, even in imagination. The debate deepened, because each side could draw strength from real observations, while still missing part of the truth. By the early 20th century, powerful telescopes had shown enough detail in some spiral nebula to make them seem more like organized systems than formless clouds. Yet there was no agreed method for placing them securely in depth. Spectroscopy had added intrigue. Vesto Melvin Slipher, working at Lowell Observatory, measured substantial radial velocities for several spirals, including the Andromeda Nebula. These speeds were strikingly large, and to some astronomers, they suggested that the spirals might be remote systems, with motions difficult to reconcile with an ordinary place inside the Milky Way. But spectroscopy alone could not settle the matter. High velocity does not automatically translate into great distance, and interpretation still depended on a larger picture that remained unsettled. At the same time, claims had been made that novae in spiral nebula seemed fainter than novae in our galaxy, which might imply enormous distances. But these too were entangled with uncertainty. The evidence was suggestive, not decisive, and the universe remained large enough to provoke argument, but not yet large enough to silence it. That uncertainty led, in 1920, to one of the most famous public confrontations in the history of astronomy. The event now remembered as the Great Debate, hosted by the National Academy of Sciences at the Smithsonian in Washington. It brought together Harlow Shapley and Heber Curtis, two astronomers whose disagreement distilled a much wider conflict over the structure of the cosmos. Shapley, drawing on his work with globular clusters, argued for an enormous Milky Way with the Sun far from its center. In such a galaxy, the spiral nebula could plausibly remain subordinate objects within the broader system. Curtis, by contrast, favored a smaller Milky Way and defended the idea that the spirals were island universes, separate stellar systems comparable to our own galaxy. Each man had evidence. Each also carried assumptions that later history would expose. What makes the Great Debate so enduring is not that one man saw the truth, while the other clung to error, but that both were partly right and partly wrong. in ways that reveal how science often advances. Shapley was right that the sun was not central, and that the Milky Way was far larger than many had thought. Curtis was right that the spirals represented systems beyond our own. The future did not vindicate one side and erase the other. It rearranged their truths into a new universe. Even so, the debate itself could not resolve the issue. Public argument, however skilled, could only carry astronomy so far without a measurement capable of fixing the spirals in space. And that required something more than analogy, velocity, or plausibility. It required a standard marker inside one of those distant nebulous forms, a known kind of light whose true luminosity could be inferred and then compared with its appearance. This was the deeper significance of the ladder built by Leavitt and those who calibrated her relation. If a Cepheid variable could be found in a spiral nebula, then its period could reveal its intrinsic brightness, and from that the distance might be derived. The problem was brutally practical. Spiral nebulae were faint. Their individual stars were difficult to separate. Measuring variable stars within them demanded powerful instruments, repeated observations, and enough patience to distinguish genuine variation from photographic uncertainty. The question of the universe's scale, once again, had become a question of whether light recorded over many nights could carry enough regularity to overturn an old world. By the early 1920s, Mount Wilson Observatory was one of the few places where such an attempt had a real chance. Perched high above Los Angeles, with its 100-inch Hooker telescope, it represented a new level of reach in observational astronomy. There, the Andromeda Nebula stood as a particularly compelling target. It was bright, extended, and structured enough to tempt the hope that individual luminous markers might be found within it. Edwin Hubble, who had joined Mount Wilson after the First World War, entered this environment with ambition, discipline, and a keen awareness of what was at stake. He was not alone in pursuing extragalactic distances, nor was he working in the vacuum, untouched by the observations and reasoning of others. But history often narrows around moments when a long accumulation of possibility suddenly becomes testable. In this case, the crucial requirement was simple to state and hard to achieve. Find a variable star in Andromeda that could be identified as a Cepheid. On the night of October 5th and 6th, 1923, Hubble exposed photographic plates of Andromeda that would become central to that effort. The physical drama of such a night is easy to imagine in broad outline, though its real importance lay in a quieter, later act. Large telescopes gather light, but discovery often arrives not at the eyepiece, but at the plate, under careful scrutiny after the observing is done. When Hubble examined those images and compared them with earlier plates, he found what he believed to be a nova, then reconsidered. The mark he wrote, VAR, captured that change in judgment. The object was variable. More observations followed, and as its light curve developed, the case for identifying it as a Cepheid strengthened. Once that happened, the chain of reasoning was ready. Measure the period. Infer the true luminosity from the period-luminosity relation. Compare that true brightness with the observed brightness. Then calculate the distance. What emerged was immense, however imperfect the early calibration might later prove. The result placed Andromeda far beyond the bounds of the Milky Way, as then understood. It was not a local cloud or subordinate structure. It was another stellar system. This was the moment when the Milky Way stopped being everything, though the phrase is more subtle than it first sounds. Hubble did not discover that the galaxy had vanished, nor did he reduce its grandeur. What changed was the frame around it. The Milky Way, already enlarged and structurally reimagined by earlier work, was now displaced from the role of cosmic totality. It became one galaxy among others. That shift is so familiar to modern thought that it is hard to recover its full force. Imagine standing in a world where the visible band of stars, the grand river of light arching across the night, had long served as the principal body of the universe. Then imagine learning that, beyond that river, lie other rivers, each vast enough to contain billions of stars. The result is not just enlargement, it is decentralization. The familiar heavens no longer form a complete enclosure around human experience. They become one local expression of a far larger architecture, and the mind must learn to live in a reality where even the galaxy is provincial. As often happens in the history of science, the first decisive answer was not the final one in numerical detail. Hubble's early distance estimate to Andromeda was too small by modern standards, in part because the Cepheid calibration itself would later be revised, but on the central issue, it did not matter. The exact number could change, and the universe would remain irrevocably altered. This distinction is important because it reveals something about how scientific understanding stabilizes. A theory or conclusion need not begin with perfect precision in order to overturn a previous world picture. Sometimes it is enough that the old interpretation becomes impossible. Once Andromeda had been placed decisively outside the Milky Way, no later refinement could return the cosmos to its earlier form. The universe had crossed a conceptual threshold from which there was no path back. The spiral nebula, or at least some of them, were galaxies. The sky had multiplied. The consequences spread quickly through astronomical thought. Objects once treated as peculiar local features became candidates for membership in a wider population of external galaxies. Observational astronomy was forced into a new task, not merely describing the contents of the Milky Way, but surveying a universe of galaxies differing in shape, brightness, motion, and distance. It is here that the emotional texture of the discovery becomes especially interesting. Astronomers did not simply gain more territory, they lost a certain kind of intimacy with the cosmos. The night sky, which had already become deep, now became populous on an almost disorienting scale. A luminous blur was no longer just a blur. It might be a vast island of stars, remote beyond ordinary comprehension. In that sense, Hubble's work did not only solve a problem, it altered the psychological atmosphere of astronomy. The universe was no longer a single city with unexplored neighborhoods. It was an archipelago without visible end. The story also invites a more careful distribution of credit than popular memory sometimes allows. Hubble became the emblematic figure in this transformation, and not without reason. But his result rested on a long chain of labor and thought. Leavitt's relation made the critical method possible. Pickering's Harvard system of photographic astronomy created conditions in which such a relation could be found and refined. Slipher's measurements had already made the spiral nebula difficult to fit inside a simple local picture. Shapley and Curtis had publicly articulated the alternatives with unusual clarity. Observers and instrument makers at Mount Wilson helped create the technical environment in which faint variable stars in Andromeda could be tracked at all. Science often appears, in retrospect, to move through single names, but the actual path is more cumulative. One of the reasons the universe became larger in the 1920s is that earlier workers had already spent decades constructing the tools, concepts, and uncertainties that made a definitive observation meaningful. At the same time, Hubble's own role should not be softened into mere symbolism. He possessed a certain exactness of ambition well suited to the era of large telescopes and growing astrophysical confidence. There was something methodical and even strategic in the way he approached observational questions that could reorder the field. He understood the importance of classification, of distance, of placing objects into a broader structure, rather than treating them as isolated curiosities. This temperament helped him turn the Andromeda result into a wider program. Once galaxies beyond the Milky Way were accepted, the next challenge was not simply to marvel at them, but to organize them, measure them, and ask whether they themselves obeyed larger patterns. The universe had become more expansive, but it had also become more available to systematic inquiry. A larger cosmos does not always mean greater obscurity. Sometimes it means that new kinds of order are waiting at scales previously unimaginable, and yet there remained, even in the wake of Andromeda, a peculiar mixture of triumph and incompleteness. Astronomers had learned that the Milky Way was not the whole universe, but they still did not know the full dimensions of this wider galactic realm. The island universes Curtis had defended were now real, but how many were there? How were they distributed? And what were they doing? The answer to one great question had opened several larger ones. This is the pattern that runs through the history of cosmic scale. Each boundary, once crossed, reveals not a finished map, but another horizon. Andromeda ceased to be a nebula and became a galaxy. The Milky Way ceased to be the universe and became one case among many. The old cosmic walls had not merely fallen, they had dissolved into a wider dark, in which new measurements would be required. One further irony deserves notice. The Great Debate is sometimes remembered as a contest settled by a single decisive observation, but real historical change is rarely so clean. Even after 1923 and 1924, assimilation took time. Astronomers still had to absorb what it meant to inhabit a universe of galaxies. The habit of thought built under an older sky does not vanish instantly, even when the evidence becomes strong. This delay between observation and deep acceptance is part of the psychology of science. A community may understand a result before it fully feels its implications. In the years that followed, as distances to more systems were explored and the extragalactic picture gained solidity, the meaning of Andromeda broadened. It was not just one external system, it was proof of a new cosmic category. Once that category existed, the universe could no longer be narrated on the scale of a single galaxy, and that expansion of category led naturally to a further puzzle, one that would soon prove even more unsettling than the discovery of galaxies beyond our own. If these external systems could be measured, then their light might reveal not only where they were, but how they moved. Slipher's earlier spectra had already hinted at unusual velocities. Now, with galaxies securely placed in the wider universe, those velocities could be reconsidered in a new frame. Distances and motions, once treated as separate questions, were moving toward each other. The cosmos had become a population rather than a solitary structure, and populations invite patterns. What no one yet fully grasped was that the next pattern would not simply enlarge the universe again, it would set the universe itself in motion. Once galaxies had been granted their own existence beyond the Milky Way, the sky changed character again. A scattered collection of spiral nebulae was now understood as a population of distant stellar systems, each occupying its own place in the darkness. That alone was enough to enlarge the universe beyond older comprehension. But it also created a new kind of problem. When something becomes part of a population rather than an isolated curiosity, comparison becomes possible. Astronomers could now ask not only what galaxies were, but how they behaved relative to one another. Were they fixed in a larger cosmic order, like islands suspended in a static sea of space? Or were they participating in some deeper motion that no one had yet fully described? This new question did not arise from philosophical speculation alone. It emerged because the tools of astronomy had finally become good enough to join two kinds of measurement that had long developed separately: the measurement of distance and the measurement of velocity. Velocity entered the story through light itself. By the late 19th and early 20th centuries, spectroscopy had become one of the most powerful ways of extracting hidden information from celestial objects. A star or nebula could appear merely as a point or a haze through the eyepiece, but its light, spread into a spectrum, carried a more intricate signature. Dark absorption lines and bright emission features revealed chemical elements. More importantly for this chapter, those lines could shift in position. If a luminous source moved toward or away from the observer, the wavelengths of its light would be compressed or stretched, producing what is now described as a Doppler shift. In practice, astronomers saw this as a displacement of familiar spectral lines from where they would appear in a laboratory source at rest. A shift toward longer wavelengths, toward the red end of the spectrum, suggested recession. A shift toward shorter wavelengths, toward the blue, suggested approach. This principle had already been used for stars, but when applied to spiral nebula, it began to hint at something much larger than local stellar motion. At Lowell Observatory in Arizona, Vesto Melvin Slipher undertook the difficult work of obtaining spectra from spiral nebulae, objects so faint that recording their light with enough clarity was a formidable technical achievement. The challenge was not simply to point a telescope and expose a plate. These nebulous spirals emitted or reflected light so weakly that the exposures could stretch to many hours, demanding extraordinary stability, careful instrumentation, and a willingness to persist through work that was slow, fragile, and often uncertain. Slipher refined the spectrographic equipment to make it more effective for such faint, diffuse targets, and over time, he began to collect results that startled the astronomical community. Beginning with the Andromeda Nebula in 1912, he found a substantial blue shift, suggesting that Andromeda was approaching soon after. Many other spiral nebulae showed the opposite tendency. Their spectra were redshifted, often by amounts so large that they seemed unlike the more modest stellar velocities familiar within the Milky Way. These were not small observational curiosities. They were hints that the extragalactic universe, if that was what the spirals truly were, might be dynamic in a new and unsettling way. At first, however, the meaning of these redshifts was far from clear. Slipher's measurements were impressive, but data by themselves do not force a single interpretation. Some astronomers treated the large velocities as evidence that the spirals were indeed distant systems, since such motions seemed difficult to reconcile with a simple place inside the Milky Way. Others were more cautious, aware that the broader framework of the universe was still in flux, even after Andromeda and other spirals were recognized as galaxies. The redshifts did not immediately announce a universe in expansion. They could still be read as the peculiar motions of remote systems moving through a larger static space. The question of cosmic architecture remained open. What Slipher had provided was something immensely valuable but incomplete, a set of clues waiting for a geometry large enough to make sense of them. In the history of science, this is a familiar pattern. A discovery may become most important only after another discovery, made elsewhere and often later, reveals what the first one had really been pointing toward. That larger geometry was emerging from an unexpected direction, not from direct telescope observation alone, but from the mathematics of gravitation on the largest possible scale. Albert Einstein's general theory of relativity, published in 1915, transformed gravity from a force acting across fixed space into a description of how matter and energy shape space-time itself. The implications for cosmology were profound, though not immediately welcome. If space-time could curve, then the universe as a whole might have a global geometry and a dynamical history. A cosmos need not be a static stage on which stars and nebulas simply drifted. Space itself might participate in the structure of the problem. Einstein, like many others, initially preferred a universe that was eternal and static on large scales, and he modified his field equations in 1917 by introducing the cosmological constant to make such a model possible. Yet the deeper mathematics of relativity did not remain confined to static solutions. Other physicists and astronomers began exploring models in which the universe could expand or contract, models in which cosmic scale itself might change over time. The old question of size was taking on a new form. The universe might not merely be large, it might be evolving. Among those who saw the significance of this more clearly than most was Georges Lemaitre, a Belgian priest, mathematician, and physicist whose intellectual temperament seems almost designed for this transitional moment in science. Lemaitre moved with unusual ease between abstract theory and observational astronomy. He was not content to let cosmology remain a formal exercise in differential equations, nor did he treat observation as something separate from deeper structure. In 1927, he published a paper in which he derived a dynamical solution to Einstein's equations and connected it to the observed redshifts of extragalactic nebulae. The universe, he argued, could be expanding, and the recessional velocities of nebulae might be understood not as ordinary motion through a fixed space, but as a manifestation of space itself stretching. In the same work, he used available distance estimates and Slipher's redshift data to infer a proportional relation between velocity and distance. The conceptual leap here was extraordinary. Lemaitre was not merely saying that galaxies happened to be moving away. He was proposing that the large-scale fabric of the universe could be in a state of general expansion. The subtlety of that idea is worth dwelling on because it marked a new level of abstraction in the human understanding of nature. In ordinary life, movement means that an object travels through space from one place to another. Lemaitre's cosmological interpretation asked astronomers to imagine something less intuitive. The galaxies need not be flying outward from a single point in pre-existing emptiness, in the simple way shrapnel flies from an explosion. Instead, the scale of space between galaxies could increase everywhere at once. Distances would grow not because the universe was expanding into some external void, but because the geometry of the universe itself was changing. This difference is conceptually delicate and remains difficult even now for many people encountering cosmology for the first time. Yet it mattered enormously. It turned redshift from a mere velocity oddity into a possible signature of an evolving universe. In that shift of interpretation, cosmic scale ceased to be a static quantity waiting to be measured. It became part of a history. Even so, Lemaitre's insight did not immediately reorganize astronomy. His 1927 paper was published in a journal that did not command the attention of the English-speaking astronomical world, and the relation between theory and observation remained fragile. Distances to galaxies were still uncertain. Redshift measurements, though growing in number, were not yet embedded in a framework widely accepted by observers. There was also a deeper cultural reason for the delay. Static cosmologies had centuries of intellectual gravity behind them. A moving universe was not merely a new numerical result. It was a change in the basic character of the cosmos. Many scientists needed not only stronger evidence, but time to adjust their instincts. What now appears as a nearly inevitable step was, in its own moment, one possible interpretation among several, and one that asked the scientific imagination to become more flexible than it had previously needed to be. That is where Edwin Hubble re-entered the story, not as a solitary creator of cosmic expansion, but as the astronomer whose observational program helped transform a theoretical possibility into a durable empirical relation. With external galaxies now accepted as real systems beyond the Milky Way, and with the Mount Wilson telescopes providing unprecedented reach, Hubble was in a position to estimate distances to a growing sample of galaxies. His work relied heavily on the distance ladder that had been built in earlier years, especially on Cepheid variables and nearby galaxies. These measurements were difficult, often uncertain, and much more laborious than later simplified accounts might suggest. Still, they were enough to begin placing galaxies in a coherent scale of remoteness. Once those distance estimates were set alongside the redshift data, many of which came from Slipher's earlier spectroscopic work and later observations by others, a pattern began to emerge. The farther a galaxy appeared to be, the greater its recessional velocity tended to be. In 1929, Hubble published this relation, giving it a clear empirical form that the astronomical world could not easily ignore. The importance of the 1929 result lay not in perfect precision, but in its structural force. Hubble's distances were not fully correct by modern standards, and the constant of proportionality he inferred was far too large. Yet the relation itself, the tendency for recession speed to increase with distance, pointed strongly toward a universe in which large-scale expansion was real. It is one of the more revealing episodes in the history of science because it shows how truth can emerge through measurements that are, in a strict numerical sense, still flawed. Astronomers did not yet possess the final scale of the cosmos, but they had found one of its governing patterns. This is often enough to change a field. Once the velocity-distance relation was accepted as significant, the old idea of a static universe became increasingly difficult to preserve. The galaxies were not simply arranged in a wider cosmos. The wider cosmos itself appeared to be stretching. The form in which this discovery entered public memory also says something about how science distributes fame. The relation became associated above all with Hubble's name, and for decades it was commonly known simply as Hubble's law. There are reasons for that. Hubble presented the observational relation with a visibility and authority that carried enormous weight, but the fuller history is more collaborative and, in some respects, more uneasy. Slipher had provided much of the essential redshift data years earlier. Lemaitre had already connected relativity, redshift, and cosmic expansion in a way of striking conceptual depth. Milton Humason, working at Mount Wilson, would soon become indispensable in pushing redshift observations to fainter and more distant galaxies. The pattern that changed cosmology was not born from one mind or one kind of labor alone. It emerged from the meeting of mathematical imagination, instrumental persistence, and the slow accumulation of data. To say this does not diminish Hubble. It restores the texture of the science. Humason's place in the story is especially telling because it reveals how physically demanding astronomy could still be, even in the age of elegant equations. Before becoming one of Mount Wilson's key observers, he had begun there in a much humbler role, and his later mastery of spectroscopic observing reflected long practical experience rather than an academic path of conventional prestige. Measuring the spectra of faint galaxies was exhausting work. It could require multiple nights, long exposures, careful guiding, and a tolerance for the uncertainty that haunts all frontier measurements. Yet it was precisely this difficult labor that allowed astronomers to extend the redshift relation outward from a suggestive pattern among relatively nearby galaxies to a deeper probe of the extragalactic universe. Humeson's observations strengthened the case that the relation was not a local anomaly, but part of the broader structure of the cosmos. Science, once again, moved not by revelation alone, but by the endurance of those willing to remain with hard data until a larger order clarified itself. As the expansion picture took hold, it began to alter the meaning of redshift itself. At first glance, a redshift might seem no more than a sign that a galaxy is moving away, like the receding sound of a train whistle dropping in pitch. But in cosmology, the interpretation had to become more nuanced. If space itself expands, then light traveling through that space is stretched along with it. The redshift of a distant galaxy is not always best imagined as a simple Doppler effect produced by motion through a static background. It can also be understood as a cosmological redshift, a consequence of the changing metric of spacetime during the light's journey. This distinction would become more important as cosmological theory matured, but even in the early period, its presence could already be felt. Astronomers were no longer just measuring where galaxies were and how fast they seemed to move. They were beginning to read the state of the universe from the behavior of light over cosmic time. That change reached beyond astronomy into human self-understanding. The discovery of galaxies beyond the Milky Way had already removed our galaxy from the role of cosmic totality. The recognition of expansion displaced something even deeper. It suggested that the universe was not a timeless order, simply waiting to be described, but a historical process. There had been earlier cosmic conditions, different from the present one. There might be future ones as well. The size of the universe could no longer be treated as a fixed backdrop to all events. It was becoming part of the unfolding story of reality itself. In retrospect, this was one of the quiet revolutions of 20th century thought. The cosmos acquired a biography. It may have been difficult to say exactly how old it was or how large it had become, but it was no longer possible to imagine it as immutable. Even then, however, the new picture carried unresolved tensions. If the galaxies were receding from one another in a general expansion, then extrapolating backward seemed to imply a denser and more compact past. Some scientists found this possibility intellectually fertile. Others found it unsettling, either for philosophical reasons or because the data still seemed too uncertain to support such a sweeping vision. Einstein himself, visiting Mount Wilson in the early 1930s and engaging with the observational evidence, moved away from his earlier insistence on a static universe, yet broad acceptance did not erase discomfort. An expanding cosmos raised questions that reached beyond the immediate evidence. How long had it been expanding? Had it begun in a finite past? Could such an expansion continue forever? These questions were not yet ready to be settled, but they had been made unavoidable. And so the universe, once measured in terms of stars, then galaxies, had become something more difficult and more alive. Distances and redshifts had converged into a pattern that transformed cosmology from the mapping of a large static structure into the study of a changing one. The sky no longer offered only positions and classifications. It offered history. Yet with this new dynamical picture came a humbling complication. The idea of expansion seemed secure enough to reshape the field, but the numbers attached to that expansion were still uncertain, and those uncertainties would soon lead to one of the most revealing problems in all of cosmology. The universe had begun to move, but no one yet knew whether they were measuring that motion correctly. The pattern of expansion had entered astronomy with enough force to change the field, but the moment its numbers were taken seriously, a troubling inconsistency appeared. If the universe was expanding at the rate implied by the early value of what would later be called the Hubble constant, then running the cosmic motion backward seemed to produce a universe startlingly young, on the order of only a couple of billion years. At first, this might have looked like a technical oddity, the sort of mismatch that accompanies any new measurement taken at the frontier of knowledge. Over time, however, it became harder to dismiss. The Earth itself, through geological reasoning and later radiometric dating, was beginning to seem older than that. A universe younger than its own planet was not merely an awkward number. It was a warning that something in the distance scale or in the interpretation of the expansion had gone wrong. And so cosmology entered one of its most revealing phases, the phase in which a grand idea survived, but its measurements did not. What made the problem so instructive was that no one had stumbled on a simple arithmetic mistake. The difficulty lay deeper in the ladder itself. The expanding universe had been recognized through a chain of reasoning that connected galaxy distances to recession speeds. But those distances were still resting on methods that had not yet fully revealed their weaknesses. Cepheid variables had given astronomy its first powerful way of reaching beyond parallax, and they had done exactly what they were meant to do. They had opened the door to the extragalactic universe. Yet once that door stood open, it became clear that the calibration beneath it remained more fragile than many had hoped. Every rung in the distance ladder depended on assumptions, comparisons, and categories that had to be right, not just in spirit, but in scale. A small misjudgment at the level of standard candles could spread upward into a cosmic error. That is the humbling architecture of astronomy. The largest conclusions often depend on the finest distinctions. At first, the urgency of the age problem was not felt in exactly the same way by every scientific community. Astronomers, physicists, and geologists were arriving at their timescales through different methods, with different degrees of confidence, and often with different instincts about what kinds of evidence should be trusted most. But as the first half of the 20th century continued, the pressure increased. Studies of radioactive decay were giving the Earth and meteorites ages of billions of years. Stellar evolution theory, still developing but increasingly sophisticated, also pointed toward timescales that were difficult to reconcile with a universe only around 2 billion years old. As a result, the mismatch became more than a curiosity. It began to look like a structural contradiction. The expanding universe could not simply be abandoned because the relation between galaxy distance and redshift was too persuasive. Yet the rate of that expansion, as then measured, seemed to force the cosmos into a timescale too short for much of the rest of science. This is one of the moments where the psychology of scientific progress becomes especially visible. Once an idea has proven strong enough to reorganize a field, researchers do not immediately throw it away when the numbers become uncomfortable, nor do they keep the numbers untouched out of loyalty to the idea. Instead, they enter a period of disciplined dissatisfaction. They ask where the interpretation might still be right, while the scale remains wrong. In the case of cosmology, that dissatisfaction fell most naturally on the distance ladder. Redshift measurements were difficult, but they were conceptually cleaner than the distances, which relied on translating apparent light into actual remoteness through a series of calibrated comparisons. If the universe looked too young, then perhaps the galaxies were actually farther away than astronomers had been assuming. If so, the slope connecting distance and velocity would change, the expansion rate would drop, and the implied age of the universe would grow. The question was not whether the cosmos moved, but whether astronomers had learned to measure its motion on the right scale. The first part of the answer emerged gradually through improved understanding of stellar populations. The Milky Way was not a single homogeneous collection of stars. Different regions contained stars with different properties, histories, and relationships to interstellar matter. This might sound, at first, like a detail belonging more properly to galactic astronomy than to cosmology. But the distance ladder had always depended on whether stars thought to belong to the same class truly did belong to the same class. A standard candle is only standard if nature has not quietly split it into multiple families. During the 1940s, Walter Baade used the exceptional observing conditions created by wartime blackouts in Southern California to study nearby galaxies, particularly Andromeda, with unusual clarity at Mount Wilson. In doing so, he distinguished two major stellar populations, later known as Population 1 and Population 2, and recognized that astronomers had been conflating stars that should not have been treated identically. This distinction reached directly into the Cepheid scale. Baade's insight altered the cosmic distance ladder in a way that was both technical and transformative. The Cepheids used for calibration in different environments did not all belong to the same stellar population, and this mattered because their luminosities were not identical in the way earlier treatments had assumed. If the intrinsic brightness of a Cepheid had been misjudged, then the inferred distance to its host system would also be wrong. Correcting the calibration effectively pushed external galaxies farther away, in some cases by roughly a factor of 2 relative to earlier scales. That did not undo the expanding universe. It did something more subtle and, in the long run, more important. It retained the structure of the idea while changing the numerical size of the world to match reality. reality more faithfully. The galaxies had not been receding too fast for the age of the universe. They had been placed too near. This is why Bod's work remains one of the most important acts of quiet repair in 20th century science. It showed that a universe can become older, not because time itself changes, but because our measurements finally become less provincial. There is something deeply instructive in the way this repair happened. The public image of cosmology often privileges the largest questions: beginnings, endings, the curvature of space, the origin of matter, the fate of all things. Yet one of the decisive steps toward a more believable age of the universe came from looking more carefully at stars in nearby galaxies and noticing that the categories guiding earlier measurements had been too coarse. Such episodes remind us that science does not advance only by asking bigger questions. It advances by sharpening its ability to tell unlike things apart. In this case, the distinction between stellar populations, combined with a better understanding of variable stars and galactic structure, had repercussions all the way out to the age of the cosmos. A classification made under the eyepiece and on the plate table could alter the time history of the universe itself. This is one of the quiet beauties of scientific reasoning. Precision in the local can rescue truth at the largest scale, even after Bod's correction. However, the work was not finished. Distance measurement remained one of the most stubborn crafts in astronomy, and the mid-20th century saw further attempts to refine the Hubble constant through better photometry, improved standard candles, and more careful treatment of biases. Alan Sandage, among others, became a central figure in this effort, extending and revising Hubble's program while maintaining a long-term commitment to reducing the uncertainty in cosmic distances. The problem was more intricate than a single recalibration could solve. Observations of distant galaxies were affected by crowding, dust, instrumental limits, and selection effects. Brighter objects were easier to detect, which meant surveys could easily favor certain kinds of galaxies or stars without fully realizing it. This led to what later astronomers would more explicitly describe as Malmquist bias and related problems, in which the visible sample is not necessarily a fair sample of the underlying population. The universe, once again, was teaching a difficult lesson. It is not enough to measure what can be seen, one must also understand what has been overlooked. This led cosmologists into a period where the range of proposed values for the expansion rate remained broad enough to support very different pictures of cosmic history. In some circles, the constant seemed high enough to imply a relatively young universe, though no longer absurdly so. In others, it was substantially lower, allowing more room for stellar and geological timescales. What mattered is that the number was no longer just a parameter on a graph. It had become a meeting point for multiple sciences. A revised Hubble constant would affect the inferred age of the universe, the scale of galaxies, and the interpretation of cosmic history. As a result, debates over distance measurement acquired an unusual intellectual weight. They were not mere technical disputes over decimal places. They were arguments about whether the great narrative emerging from cosmology could coexist with the rest of natural knowledge. In this sense, the age crisis did not weaken cosmology. It forced cosmology to mature. Maturity in science often means learning that the first successful method is rarely the final one. Cepheids remained indispensable, but they also had to be placed within a broader web of indicators. Astronomers compared different kinds of variable stars, the luminosities of brightest stars and galaxies, the properties of star clusters, and later a growing set of secondary distance indicators. Each method carried its own strengths and vulnerabilities. Some worked well nearby but failed at great distance. Some depended on assumptions about galactic environments. Some were sensitive to dust or metallicity, features that could subtly alter brightness and color. The more the distance ladder expanded, the more the ladder itself became an object of scrutiny. Astronomers did not simply climb it. They tested each rung, asking whether it bent under weight, whether it was anchored securely, whether one calibration could truly support the next. This may sound cautious to the point of obsession, but such obsession is often what separates a beautiful idea from a durable science. At the same time, the age problem revealed something philosophically important about the relation between theory and observation. A weaker scientific culture might have treated the expanding universe as discredited, because its first age estimate clashed with other evidence. A more dogmatic culture might have forced the rest of science to yield to that first estimate. What actually happened was more interesting. Cosmology, geology, and stellar physics pressed against one another until the contradictions became productive. The Earth's apparent age challenged the cosmic timescale. Stellar theory made that challenge harder to ignore. In response, astronomers returned to the latter and improved it. The universe, once thought to be embarrassingly young, became older as the distance scale grew more accurate. The intellectual result was not merely a corrected number, it was a demonstration that truth in science often emerges from tension between disciplines rather than from the isolated triumph of one. There was also a more intimate consequence to all of this. The early discovery of expansion had given the cosmos motion, but motion alone is not yet a believable history. To tell a plausible story about the universe, astronomers needed a timescale large enough to contain stars, galaxies, and the Earth itself. Once the expansion rate was lowered through better distance measurements, the universe began to look less like a dangerously compressed event and more like a vast, evolving system with room for structure to form. This did not resolve every difficulty. Important uncertainties remained, and the exact value of the Hubble constant would continue to be debated for decades. But the broad lesson had already taken hold. The first numbers had been too small in scale and too large in rate. The cosmos was larger, and therefore older, than the earliest expansion measurements had implied. In a curious way, the universe had to be given back some of the time that poor calibration had taken from it. Yet that recovery of time also did something else. It made the implications of expansion harder to avoid. When the universe seemed only a couple of billion years old, one could still suspect that some basic measurement flaw might someday collapse the entire picture. As the numbers improved and the age problem softened, the expanding universe began to look less like a fragile novelty and more like the permanent setting for a larger argument. If galaxies were receding from one another and had been doing so across immense stretches of time, then what did that imply about the past? Had the universe once been smaller, denser, hotter? Or was there some way to preserve a cosmos without a true beginning, one that expanded while maintaining an overall steady character? The correction of these numbers did not end cosmological debate. It clarified its real stakes. Once the scale became more believable, the argument could move beyond measurement alone and confront the deeper question that had been waiting behind it all. What kind of history did an expanding universe actually have? Once the numbers of expansion began to look more believable, the old discomfort returned in a sharper form. A universe that grows larger over time seems almost against our will to invite the mind to run the process backward. If galaxies are now farther apart, then there must have been a time when they were closer together. If the scale of the cosmos changes, then the present arrangement of stars and galaxies cannot be eternal in the simple static sense that earlier centuries had imagined. This did not yet tell astronomers exactly what the beginning of the universe looked like, or whether the word beginning was even the right one. But it changed the emotional center of cosmology. The universe was no longer just a vast structure with a measurable age problem. It was becoming a historical entity, something whose present state implied a past unlike the one visible around us. And as soon as that thought took hold, the deepest question in the field came into view. Was the cosmos born in some finite moment of origin, or could it somehow expand forever while remaining, in a larger sense, timeless? That question had already touched Albert Einstein in an earlier and more guarded way. When general relativity first opened the possibility of a dynamic universe, Einstein did not greet that possibility with enthusiasm. Like many thinkers of his generation, he was drawn to the idea of a cosmos that was stable on the largest scales, neither collapsing under its own gravity nor flying apart in a way that seemed to suggest a cosmic history. In 1917, when he applied his field equations to the universe as a whole, he found that a simple static solution did not hold under the attractive pull of gravity alone. To stabilize it, he introduced an additional term, the cosmological constant. In mathematical form, it was elegant enough, but philosophically it served a clear purpose. It allowed the universe to remain large, eternal, and globally unchanging. There is something revealing in that move. Even Einstein, whose theory had reimagined space and time more radically than almost anyone before him, still hesitated before a cosmos that might have to change in its deepest structure. Yet the universe had little interest in preserving human preferences, as Friedman and then Lemaitre explored solutions to the relativistic equations without forcing staticity. The possibility of a changing cosmos became harder to dismiss. Einstein at first resisted some of these models, but resistance is not the same as refutation, and the observational evidence slowly shifted the balance. Once galaxy redshifts and distances seemed to align with large-scale expansion, the old static picture began to feel increasingly artificial. The cosmological constant, originally introduced to hold the universe still, came to seem less like a natural feature of reality and more like a mathematical device placed into the equations to rescue a philosophical hope. Later generations would attach a famous phrase to Einstein's discomfort about this episode, though the exact wording and tone are historically less simple than popular retellings suggest. What matters more is the intellectual trajectory. The greatest theorist of the age had attempted to preserve a changeless cosmos, and the cosmos itself had answered by continuing to move. As a result, by the middle decades of the 20th century, cosmology was no longer debating whether the universe was dynamic. It was debating what sort of dynamical thing it was. One possibility, increasingly developed by George Gamow, Ralph Alpher, Robert Herman, and others, imagined an early universe that had once been much denser and hotter than it is now. In this picture, the present expansion was the aftermath of a primordial state in which matter and radiation had existed under extreme conditions, and some of the basic features of cosmic composition might have been forged in that early environment. This was not yet the polished modern Big Bang theory taught in classrooms. It was a developing framework, full of uncertainties and still entangled with unresolved questions about element formation, cosmic age, and the details of observational evidence. But it offered something powerful. It treated the expanding universe not as a mere kinematic fact, but as a clue to origin. Expansion was no longer just motion, it was memory at almost the same time. However, a rival vision emerged that was intellectually serious, elegant in its own way, and appealing to many scientists precisely because it resisted the idea of a finite beginning. In 1948, Hermann Bondi, Thomas Gold, and Fred Hoyle proposed what became known as the steady-state theory. Their universe also expanded. But unlike the evolutionary models associated with a hot, dense past, it remained statistically the same on the largest scales through time. New matter would be continuously created, in very small amounts, just enough to keep the average density of the universe constant as galaxies moved apart. This was not meant as a theological or mystical alternative. It was a physical proposal, and one motivated partly by a philosophical principle that Bondi and Gold called the perfect cosmological principle. According to that principle, the universe should look the same not only in every direction and every location, on sufficiently large scales, but also at every epoch. A truly steady universe would have no privileged moment of origin. It would be, in its deepest character, the same kind of universe forever. There was an undeniable attraction to this idea. It offered a cosmos without the conceptual embarrassment of a beginning, without a first instant that seemed to invite questions physics could not yet answer. It also preserved a kind of serenity. In a steady-state universe, change happens locally and continuously, but the whole retains its overall character. One can see why this would appeal to scientists who disliked the notion of an initial cosmic event from which everything emerged. Fred Hoyle, in particular, became one of its most articulate defenders, combining astrophysical sophistication with a sharp rhetorical instinct. It was Hoyle who, during a 1949 radio broadcast, referred to rival evolutionary cosmologies as the Big Bang idea, a phrase that would outlive its original context and become the dominant name for the very model he opposed. The irony is almost too perfect. One of the most famous terms in modern science entered the public imagination from the mouth of an intellectual adversary. For a time, the contest between these two broad visions was real, and open. This is important to remember, because later retellings can make the triumph of the hot Big Bang seem inevitable. It was not. In the 1950s, cosmologists still lacked many of the decisive observations that would later define the field. The universe was difficult to survey at great depth. Radio astronomy was opening new windows, but also producing new confusions, and the relation between theory and evidence remained incomplete. In that environment, the steady-state model had genuine strengths. It was simple in certain respects. It handled expansion without requiring a singular beginning, and it offered a philosophically clean picture of the cosmos. The hot Big Bang approach, by contrast, had explanatory promise, but also sharp, unanswered questions. How exactly had the chemical elements formed? What relics of the early dense state should still exist? Could such a model be tested by anything more than broad consistency with expansion? The argument was not between reason and irrationality. It was between two different tastes in cosmic explanation, both still seeking decisive contact with observation. What gradually tipped the balance was not a sudden collapse of one theory under pure logic, but the appearance of evidence that a hot early universe ought to have left behind. If the cosmos had once been dense and hot enough for matter and radiation to interact intensely, then as the universe expanded and cooled, that radiation should not simply vanish, it should persist, diluted and shifted to much longer wavelengths, filling space as a faint background glow. George Gamow, together with Alpher and Hermann, had anticipated something of this sort in the late 1940s, estimating that a relic radiation from the early universe might still be detectable at a low temperature. The prediction did not immediately reshape astronomy, partly because it was not obvious how such a signal could be found, and partly because cosmology itself was still a relatively small field. But the idea lingered. If the universe had a hot past, then the present sky should contain a whisper of it. The discovery of that whisper came in 1964 through an encounter that was, in one sense, accidental and, in another, historically prepared. Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, were using a sensitive horn antenna for radio and microwave measurements when they encountered an excess noise that seemed to come from every direction in the sky. They checked their instrument, their electronics, the environment, and even the possibility that physical contamination in the antenna might be contributing to the problem. The signal remained. It did not depend on where they pointed. It did not disappear when ordinary sources of interference were removed. At roughly the same time, a group at Princeton led by Robert Dicke was thinking seriously about the possibility of detecting relic cosmic radiation predicted by a hot early universe. When the connection was made, the meaning of the Bell Lab signal became difficult to escape. Space itself appeared to be filled with a microwave background, nearly uniform across the sky, corresponding to a temperature of only a few degrees above absolute zero. This changed cosmology because it was the kind of evidence neither side could absorb equally well. A pervasive microwave background was natural, even expected in broad outline, within a hot Big Bang framework. It was much harder for the steady-state model to explain convincingly as a global feature of the universe. The importance of the cosmic microwave background was not merely that it supported one theory over another. It gave cosmology a new kind of observational anchor. Until then, many of the great questions about origin and cosmic history had still floated in a realm where theory and sparse data met uncertainly. The background radiation made the early universe observable in principle, not directly, as one sees a nearby star or galaxy, but through relic light that had survived from an unimaginably earlier state of cosmic evolution. The universe, for the first time, seemed to carry within itself a detectable fossil of its youth. Still, the full force of that fossil did not emerge all at once. The background radiation discovered by Penzias and Wilson was compelling, but much about it remained to be measured more precisely. Was its spectrum truly that of thermal radiation from a hot early universe? Was it perfectly uniform, or did it contain tiny irregularities that might later grow into galaxies and clusters? Over the following decades, these questions became central, and they pushed cosmology toward an increasingly quantitative form. The old philosophical debate over whether the universe had always been roughly the same or had evolved from a radically different past was now being recast in terms of specific measurable features of radiation, matter, and structure. That transition is one of the most important in the whole history of the subject. a question once argued in large conceptual strokes, was becoming answerable through precision observation. In this sense, the downfall of the steady-state model was not abrupt humiliation, but gradual exclusion from the growing weight of evidence as radio source counts, quasar observations, and above all the microwave background accumulated. The case for a universe that changes substantially over cosmic time became more difficult to resist. The steady-state picture had insisted that, on sufficiently large scales, the universe should look statistically the same at every epoch. Yet the deeper astronomers looked, the more they saw signs of cosmic evolution. Distant regions, because their light came from earlier times, did not present quite the same universe as the one nearby. The sky itself had become historical. This is what the expanding universe had been hinting from the start, but only now could the hint be supported with something like a record. The cosmos had not merely grown, it had changed, and it had left evidence of that change behind. There is a broader intellectual lesson here as well. Human beings often imagine scientific revolutions as moments when one decisive proof sweeps away all prior uncertainty. In practice, the shift is usually more layered. The Big Bang model did not triumph because one dramatic image forced universal surrender. It triumphed because the series of theoretical expectations and observational discoveries began to fit together more naturally than their rivals. Expansion implied a denser past. A denser past implied relic radiation. Relic radiation was found. The discovered background had properties increasingly consistent with thermal origin. The universe seen at great distance appeared different from the nearby universe in ways that undercut the steady-state ideal, taken one by one. These developments might still have been contested or reinterpreted. Taken together, they formed a new kind of coherence. In science, coherence is often what transforms an idea from possibility into framework. Yet even at this stage, cosmology had not reached its final form. To say that the universe had a hot, dense past was not to say that every aspect of its history was now understood. Important problems remained. The age of the universe still depended on the exact expansion rate. The formation of large-scale structure still required explanation in detail. The origin of the slight irregularities that allowed matter to clump into galaxies was not yet fully visible, and the microwave background itself, though now recognized as central, had to be measured with far greater accuracy if cosmology was to become a precision science rather than a persuasive narrative supported by broad observational strokes. The old argument about whether the universe had a beginning was largely resolved in one direction, but the work of reading the universe's earliest surviving light had only just begun. The next chapter would not be about whether the cosmos had a past. It would be about how much that faint ancient radiation could tell us, and how precise the modern portrait of the universe might become once we learn to listen to it properly. The ancient radiation of the cosmos, once detected, did not remain a vague background for long. It invited a more exact kind of listening. If the microwave sky truly preserved the afterglow of a hot early universe, then its details should contain more than a general confirmation that the cosmos had once been denser and hotter. It should carry encoded information about the composition, geometry, and age of the universe, written not in words, but in tiny differences of temperature across the sky. At first, those differences were expected in theory before they were actually observed. A perfectly uniform universe would have offered no easy path toward the structures we see now. No natural seeds from which galaxies and clusters could grow. So cosmologists looked for minute irregularities, fluctuations so slight that they required technology of extraordinary sensitivity. The search was difficult not because the signal was absent, but because it was buried inside the challenge of measuring a sky whose variations were almost impossibly small. Yet once the effort began, the microwave background started to become something more than evidence for a hot beginning. It became a map of the early universe itself. This transformation entered a new phase with the Cosmic Background Explorer, or COBE, launched by NASA in 1989. By then, cosmology had matured enough to know what it wanted, but not yet enough to claim it had found it. Kobe carried instruments designed to test two crucial aspects of the background radiation. One would measure the spectrum with great precision, asking whether the cosmic microwave background was truly the relic thermal glow predicted by the hot Big Bang model. Another would search for anisotropies, the tiny temperature variations across the sky that would later feed the growth of structure. The results were profound in exactly the calm, technical way science often changes the world. Kobe showed that the spectrum of the microwave background was astonishingly close to that of a near-perfect blackbody, confirming with remarkable precision that this radiation did indeed come from a hot, early phase of cosmic history. Then, in 1992, the satellite revealed the long-sought anisotropies, fluctuations at the level of tens of microkelvin. They were minuscule in absolute terms, but conceptually they were immense. The early universe was not perfectly smooth. It contained the faint unevenness from which later cosmic structure could emerge. That discovery did more than vindicate a theoretical expectation. It changed the feel of cosmology as a discipline. For decades, the subject had moved through large claims, supported by expanding but still limited evidence, and for that reason, it often drew suspicion from scientists in neighboring fields who saw it as too speculative, too dependent on sparse data, and too vulnerable to grand storytelling. Kobe began to alter that reputation. A field once associated with broad pictures of origin was becoming something stricter, more numerical, and more precise. It is one thing to say the universe had a hot, dense past. It is another to measure the spectrum of its relic light so accurately that alternative explanations collapse under the weight of the data. It is one thing to infer that structures must have grown from small irregularities. It is another to detect those irregularities directly with COB. The universe no longer offered only an ancient glow, it offered a pattern, and patterns, once measured, can be interrogated. They can be modeled, compared, and used to constrain the deeper properties of reality. That naturally led to a more ambitious question. If the microwave background contained a record of the young universe, then perhaps its pattern could reveal the overall shape of space itself. This is where cosmology began, asking a question that sounds deceptively simple, but carries extraordinary consequences. Is the universe spatially flat, positively curved like the surface of a sphere, or negatively curved in a saddle-like way? In general relativity, these are not merely geometric curiosities. They are tied to the total energy density of the universe and to its long-term evolution. For much of the 20th century, such questions remained more theoretical than observational. But once the anisotropies of the microwave background could be measured, the early universe became a kind of acoustic system. Pressure waves in the hot plasma before the formation of neutral atoms left an imprint in the angular scale of those fluctuations. By measuring the characteristic size of the pattern on the sky, cosmologists could infer the geometry through which that ancient light had traveled. In a strange and beautiful sense, the universe had preserved its own ruler. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, entered this scientific landscape like a patient cartographer. It did not merely confirm that anisotropies existed, it mapped them across the full sky with much greater precision than COBE, transforming broad hints into a detailed cosmological dataset. Over the years that followed, WMAP helped establish what would become known as the concordance model of cosmology. The universe appeared to be about 13.7 to 13, 8 billion years old. Its large-scale geometry appeared very close to flat, ordinary matter. The matter that makes stars, planets, gas, dust, and bodies seemed to account for only a small fraction of the total cosmic budget. The rest belonged largely to two stranger components, dark matter and dark energy. This was one of the more humbling turns in the history of science. The same species that had once imagined the visible stars as nearly all that existed was now forced to accept that the luminous universe is only a thin surface on a much darker and more obscure whole. Precision, in this case, did not produce familiarity. It produced estrangement of a more disciplined kind. Then came Planck, the European Space Agency mission launched in 2009, which pushed this work to an even finer level. If WMAP had given cosmology a reliable high-resolution portrait, Planck offered something closer to a forensic image of the early universe. The mission measured the temperature and isotropies and polarization of the microwave background with extraordinary sensitivity, and from those measurements derived some of the tightest constraints yet on the basic parameters of cosmology. The age of the universe sharpened the proportions of ordinary matter, and dark energy became more tightly bounded. The large-scale geometry continued to appear remarkably close to flat. To listen to the language of cosmology in the Planck era is to hear a discipline speaking with unusual confidence about the first few 100,000 years after the Big Bang. There is something almost paradoxical in that. We know the early universe, in some respects, better than many later chapters of cosmic history, because its relic light fills the sky with extraordinary fidelity. The far past survives in a form that can be measured everywhere at once, and yet the closer cosmology came to precision, the stranger the content of the universe appeared. Ordinary matter remained a minority component, roughly 5% of the total. Dark matter, invisible but gravitationally influential, accounted for far more, and dark energy, the most enigmatic term of all, seemed to dominate the present-day cosmic energy budget. The rise of dark energy as a central idea came not from the microwave background alone, but from another stunning turn in the story of cosmic expansion. In the late 1990s, teams studying distant Type 1, a supernovae, expected to measure how much the expansion of the universe had slowed over time under the pull of gravity. Instead, the supernovae appeared dimmer than anticipated, which suggested they were farther away than a decelerating universe would predict. The implication was unsettling. Cosmic expansion was not slowing. It was accelerating. In broad conceptual terms, the universe had not merely begun to move. It was being driven apart ever faster. The observational logic behind that result was delicate and, for that very reason, persuasive. Type 1a supernova, while not absolutely identical in their raw properties, can be standardized through careful analysis of their light curves and spectra, making them powerful indicators of distance across cosmological scales. By comparing their inferred distances with their redshifts, astronomers could reconstruct how the expansion history of the universe had changed over time. What emerged was not the graceful slowing expected in a universe governed only by gravity and matter. Instead, the data pointed toward an additional component acting in the opposite direction on cosmic scales. Dark energy was the name given to this effect. Though the word explanation would be too strong, it functioned as much as a label for ignorance as for understanding. The cosmological constant, once introduced by Einstein to keep the universe static, and later treated as an embarrassment of theory, returned in altered form as one of the simplest ways to model the new acceleration. History, as it sometimes does in science, folded back on itself. By this point, the question of how big the universe is had become inseparable from what kind of universe it is. Expansion, geometry, matter content, dark energy, and cosmic history all fed into one another. But perhaps the most difficult distinction of all still remained the one we began with in simpler form. The difference between the observable universe and the whole universe. The observable universe is not defined by a wall in space, nor by a shell of matter, nor by an edge where things simply stop. It is defined by light travel time within an expanding cosmos. There are regions from which light has had time to reach us since the early universe became transparent, and there are regions from which it has not, because space has expanded during that travel. The present-day distance to the furthest matter we can in principle observe is much greater than the naive light travel time alone would suggest. This is why the observable universe is not merely 8 billion light-years in radius. It is vastly larger. The visible horizon is a consequence of cosmic history, not of a physical boundary like the shore of an island. That distinction matters because it changes the emotional meaning of the sky. In older cosmologies, a boundary might at least be imagined, a final shell, a limit one could picture. The modern horizon is subtler and more haunting. It is not the end of the universe. It is the end of causal access. Beyond it, there may be more galaxies, more large-scale structure, perhaps an almost endless continuation of the same general cosmos. But if light from those regions has not had time to reach us, and never will, because of the ongoing expansion and acceleration of space, then they remain outside our observational world. Science does not say that such regions are unreal. It says something more austere. They may be real, but they are not part of what we can directly test. In that sense, the observable universe is both immense and incomplete. It is the largest reality available to observation, and possibly only a small province of the total. There is another difficulty here, one that can sound at first like a contradiction. until the deeper geometry of cosmology is understood. Galaxies at sufficiently great distances can recede from us at an effective rate greater than the speed of light. And yet this does not violate special relativity in the ordinary sense. Nothing is locally outrunning light through its own surrounding space in the familiar way a rocket or particle might attempt to do. Rather, the large-scale metric expansion of space increases the separation between distant regions so rapidly that the effective recession can exceed that limit. This is one of those moments where the intuitive imagination, shaped by the scales of daily life, has to loosen its grip. The universe is not a collection of objects moving through a pre-existing static container. The container itself, insofar as that metaphor can be used at all, is dynamic. Distances are part of the history. As a result, asking how large the universe is means asking about a reality in which space, time, motion, and access are inseparable. For a while, it seemed that this precision era might finally settle the most important cosmological numbers into a stable and satisfying agreement. Planck's measurements of the early universe gave a value for the Hubble constant, the current expansion rate of about 67 kilometers per second per megaparsec, within the standard cosmological model. Meanwhile, astronomers working in the more local universe, using Cepheids, supernova, and related methods tied to the late-time distance ladder, increasingly reported higher values around the low to mid-70s. At first, many scientists hoped this discrepancy would shrink as methods improved. Minor tensions are common in measurement science, especially when one method infers a present-day quantity indirectly from the early universe, while another tries to measure it more directly in the nearby cosmos. But over time, the mismatch refused to disappear. It sharpened. This became known as the Hubble tension, and it introduced one of the most intriguing final twists in our story, the more precisely cosm. By the end of this journey, the question that first seemed so simple no longer feels simple at all. The size of the universe is not just a matter of distance. It is tied to time, to light, to motion, to the limits of observation, and to the strange fact that the cosmos we can see is not necessarily the whole cosmos that exists. What began as a search for scale became something quieter and more profound, an encounter with this difference between reality itself and the portion of reality that has had time to reach us. That change in understanding reshaped far more than astronomy. It altered humanity's sense of place. The Earth ceased to be central, then the sun, then even our galaxy, again and again. Science asked us to step back from the comforting dimensions of everyday life and inhabit a universe measured in millions, then billions, then horizons beyond direct experience. Yet there is something deeply human in that widening. The same species that once looked up and imagined a fixed canopy of stars learned, through patience and error and revision, to read the age and geometry of the cosmos from faint light crossing unimaginable distances. And perhaps that is the most lasting meaning of this story. Scientific curiosity does not conquer mystery so much as refine it. Each answer makes the universe more intelligible, but also more subtle. Each measurement sharpens the outline of what remains uncertain. Somewhere beyond the galaxies we can map, beyond the relic light we can detect, beyond the present reach of our instruments and equations, the larger reality still waits. And so the search continues, not because we are close to the end, but because the act of looking has always been one of the ways human beings learn the true scale of their own wonder.